Hello everyone. Today I'll be trying to do something that I just thought about now as I was trying to put my daughter to sleep and had been there for over an hour. I'm just gonna try to wing it. I'm going to try this the first time. Let's see how it goes. I always wanted to use the attractor point in Revit to create an adaptive component that it can change by proximity with another element. But I would like to do that not just with a point, I would like to do that with a line. I could try to do multiple attractor points by creating a bunch of parameters and formulas, but eventually what I would get would be this. This is an interesting blog I found, but in Revit I would get the same result. This is not what I'm looking for. You can see here that measuring the distance from multiple points could only give me this circular textures, and I wanted something more fluid, something more like this. Give it a try. So I'm in a plan view. I'm going to create an in-place mass. So going to mass in place, and I'm going to start with the reference plane. Reference plane shortcut is RP. It's there, but I tend to use shortcuts for everything. And create two reference planes. I still don't know if I'm gonna need them because I'm just winging it, really. So if I draw a line here and I extrude it, create form, go to a 3D view and WT to Windows tile, and I'll divide this surface. You could use any pattern really, but for now this will work. We want to create a pattern that probably, well, as an advice, the first time you're testing something, keep it smaller so that it doesn't take forever to load, and when you see it works, we can increase that number. So we're gonna do a panel to place here, and we'd like that panel to be modified not only by an attractor point. Usually this would be done by placing a point on the other side, and any panel that's closer to this, it will open or close in a different way. This time what we're gonna try to do is actually create a surface. I'm going to open the east relation. So let's set the work plane to right. It's okay. Let's start drawing spine here. I guess we can go a bit higher, just erase that one. So if we have this line selected and we copy this a few times, just click multiple so we can just create one more. And select the reference point so I only have the lines. Let's make these reference line so we can actually see them better. And let's create form. Now we select the face, we divide it by the same number as the other one, and we have the two surfaces. So what we would like it to happen is that we modify this one, but basically the interaction that we want, instead of a tractor point, we want the panels that we'll place here to change according to some wavy and varying distance from this side. So something like this should do. Well, the waving job for later, when we actually have the panel making the movement that we want, so we can see if it's doing what we want or not. Anyway, it's doing this thing here. I'm just gonna select all these, and all these, and move them all back. I think it might be okay. Well done. So the family that we will create, if we go to new family, usually we would do a generic model pattern based, but to do an attractor we need to use the generic model adaptive. Place 4 points, 5 points, and make them adaptive. And I'm going to, so if you do this, you'll see that if we load the family into the project, we go to the 3D view. Let's look at the surface again. Let's go to this option here. It gives you a few more options about the surface, and we can tick the nodes on, so we have the placement points for our panel. So we go to nodes again, and if I do shortcut for the component, so 1, 2, 3, 4, and our 5th one will go in here. Repeat. You'll see that it's repeated across the two surfaces, and this line is having a different size according to our wavy surface. So this is one that we're going to use to measure our opening change. So let's do that. We don't need this right now, but we can leave it on. We don't have to place it again. So let's go back to our family. So what are we going to do? I'm gonna get rid of this one, all the others. I'm gonna make a reference line, and I will try to make something interesting. So if I make a reference line here, maybe we place a point here in the middle, another one there. So if we set the work plane to be a plane on this reference line, and we place a dimension from the point, don't pick the planes, pick only the points. Let's say that this will be the one that we're going to be measuring from. So it's going to be our calc length, whatever it is, instance, and we do have to tick reporting parameter because we're going to use it just to read the distance. So now we select these. Actually, I'm going to try to make this a bit more interesting. Let's pick the 2 points, select always here. So we place another point, and we're going to set this one. It's okay, just saying that there are identical points in the same place, it's okay. Now we have 2 points. If we give it an offset, apparently minus. And I'm going to create reference lines to this point and tick to make them reference line. So again, and what this will do is that it will give it a height so it's not completely flat, and we'll place other points hosted on the line, and now we'll create our face. And create face. Nice. So if we select this point that was hosted in the reference line, we'll see that it has this normalized curve parameter. And the way it works is that when it gets to one end of the line, it goes closer to 0.7, and when it comes to this end, it goes to 0.03. So what it's doing is measuring values from 0 to 1 from the end to the beginning, from the beginning to the end of the line. So that's what the normalized curve parameter is. So if we see that if it's at 0.5, it will be at the middle, at 0.1, near the beginning. So if we place both at 0.1, we'll see that they actually are measuring in different directions. So we're going to say that this is set a parameter for this one, say normalized curve parameter, make it instance, so we can change for every instance. And okay, but this one we won't be able to use the same parameter because it's actually inversed. So we'll say NCP inverse. And we'll go to the properties. And this inverse will say that it needs to be 1 minus NCP. So when that one is 1.1, this one will be 0.9. When this one is 0.9, this one will be 0.1. 0.5, 0.5. So we can check if it's working. And it is. The only thing to bear in mind is that this can't be 0, because in this case, if it will get to here, if you apply, it would say unable to create form, because what's happening is you're pulling it all the way here, so this face of the triangle would be 0, so it wouldn't exist, so it's not able to create the surfaces, so it can never really be 0. It can be 1 though, that wouldn't be a problem, but it can't be 0. Let's keep it like this. So I'm thinking after it goes, to give it a little bit more movement, make it a bit more interesting, I'm thinking that the panel will change from all open there to closed and then to flat. So we can add one extra movement just by making this point that has an offset, making this point move too. So if we select this and create an offset parameter and give this one the same parameter, now we have that too. So what do we want to do? If this length changes, that our panels will open and close with it, what we have to create is create the formulas that will accomplish that. And I'll try to show you how this is going to work. For instance, we have a normalized curve parameter that goes from 0 to 1 that will work the opening and closing of this panel. Then we have a length, that is this calculated length. It's being measured from our adaptive point, and we have to establish what this number is going to be. If we have the plane where our panels are being placed, and we have a curved surface that we'll manipulate to change the form, we'll have to know how much we're going to deform this surface so we can give it an approximate number. So let's say that this length will be up to 8,000, meaning that anything above 8,000 won't transform our panels anymore. So we want this normalized curve parameter to vary between 0 and 1 when this calculated length changes from 0 to 8 meters. So the math. So if we have a range A and a range B, so if we divide 500 by 5, that will equal 100, which will be the same as 5 equal 500 divided by 100. So if A is what we want to know, and if B is our variable, we'll say that A equals B divided by 100. If we change this, let's say the range now that we want to work with is from 0 to 350, the same thing will happen. 350 divided by 5 equals 70. Our formula will be that A equals B divided by 70. Then if our range starts at 50, then it gets a bit more complicated. We can't just divide 350 by 5. What we want is the range, and the range is between 50 and 350 is 300. So it means that what we want is 350 minus 50 divided by 5, and that will equal 60. So the formula that we'll have to use is that A, value that we want, equals B, our variable, minus 50 divided by 60. For instance, let's try to apply it to our exercise. So our normalized curve parameter should go from 0 to 1, and our length will vary between 0 and 8,000. So 8,000 divided by 1 equals 8,000. So our normalized curve parameter will equal the calculated length divided by 8,000. For instance, if our length from one surface to the other would be 500, 500 divided by 8,000 would equal 0.06. So our normalized curve parameter will be almost 0, and it would appear like this. If, for instance, our length would be 8,000, 8,000 divided by 8,000 would be equal to 1, so our panels will be completely shut. But every value that's above 8,000, the normalized curve parameter would continue to increase and go to 1.2, 1.5, and so on. And the normalized curve parameter doesn't work, wouldn't allow that, would give you an error. So what we have to do is apply an if statement that's really not that complicated. If we think the end result is the if true value, and this is the formula that we did, calculated length divided by 8,000, we just have to check with the argument that every time that the length exceeds 8,000, the normalized curve parameter will still be 1. So the argument says that if the calculated length divided by 8,000 is still below 1, use the formula calculated length divided by 8,000. But if not, meaning it's above 1, then we want the value to be 1. So this is the formula that we're going to use in the normalized curve parameter. Then there is the second part. The offset is going to change and flatten out the panel after the 8,000. So we need to establish a range for that as well. Let's just say that as the length increases 2,000 more, then our offset will decrease until 0 when it flattens out. So now if we try to apply the same formula, so we'd have to say 10,000 minus 8,000 divided by 0, but that would give you 0 as well, so it doesn't work. So to do this, we can work from the top and reverse the order. We have to say 8,000 minus 10,000 divided by 400, and this would equal minus 5. So this is the formula that we want. So when the calculated length would be 8,000, would mean 8,000 minus 10,000 would be minus 2,000, divided by minus 5 will be equal to 400. If our length would be 10,000, minus 10,000 divided by minus 5. So we have two if statements, one inside the other, because we have two arguments. The first one says that if the length exceeds 10,000, then we want it to remain flat. So if true, it will be 0. The offset will be 0. The second argument will tell you that if the length is less than 8,000, then if true will remain as 400. If not, it will mean that it's between 8,000 and 10,000, and the formula that we came up with before, it will apply, that the length minus 10,000 divided by minus 5. And this is the formula that we have to apply to the offset parameter in the family. So let's go back to the family. Let's paste these formulas. I've actually made the formula a bit different, because as I was working the family I did it out of the top of my head, but when I went back to build the presentation now, I made it neater. So now let's paste it here, in the first formula in the normalized curve parameter, and the other one in the offset, and we'll do OK. We can just drag this point up and down to check that it works. And it's all working properly, so let's just load it into the project. This is something that happens, that when we load and the repeated component has been already placed, we have to go to undo and redo again. Just a silly problem that Revit has. We can see that our panels are not being modified. And I can check in the elevation that this distance here is more than what we accounted for. That should be always under 10 meters. So I'm just going to drag them closer, and you see that it starts changing our panels. If I select the surface and we change the grid spacing, maybe this was too much, but we can see that we'll have a much more interesting result. So I'm going to place one panel here, the 4th point and the 5th point on the other surface. So if I hit repeat, it may take a little bit because I divided the surface too much, but you will see that what we got is a pattern that's not changed only by distance to one point, making just a circular pattern effect, but it's something a lot more organic. So quite interesting. Now all we have to do is just play with the surface behind and make as many lumps as we will, or make this change more gradient, however we like, just by changing our surface. And the end result will look something like this. So we can see that we can achieve different results, and it doesn't have to be very centralized to one particular point, which I think is quite interesting. So thank you for watching, and see you next time.